Okay, welcome to your free GRE prep hour for January 16th, 2024. I'm Dmitry. Hi. Today we're going to talk about some ways to review, but also the kind of stuff we can get out of a problem when we spend a little more time with it, trying to understand what it represents, what it's giving to us, and how we can connect it to other problems. I see a lot of people just kind of plowing through material. They do problem after problem after problem, but they don't always get what they need. And then other times I have students kind of frustrated by a harder problem because they say, how on earth was I supposed to think to do this in, less than 2 minutes? How was I supposed to come up with this? What kind of genius do they think I'm supposed to be? And I don't think, if you're a genius, that's great. It's certainly nice and helpful for you, right? But I don't think you need to be a genius to get most or even all of the GRE questions correct. A lot of it's more just about recognizing the task, knowing what you're supposed to do. Just like I don't have to sit there and, invent division, right? To do division problem, right? Someone's figured that out for me, right? Whether I'm using a calculator or long division, the work of people who have come before me is definitely going to help me there, right? I don't have to think about setting a quadratic equal to zero and, finding the roots that way, right? That's some clever thing someone else thought of. There are a lot of very specific things I can learn to recognize in problems and say, oh, they're testing this, and I can adjust that depending on, what question I'm doing and what exactly else they ask me to do to get some principles out of it. So that's what I'm trying to do. And a lot of times I find myself trying to slow people down. Not on the test where I'm always trying to go, hey, let problems go. If it's not going to happen in 2 minutes or less, get out of there, right? But in your review, do fewer problems, basically. Do fewer problems and really understand the problems that you're doing and get something out of them. And if you're studying for long enough, then you'll get to plenty of problems, right? That's fine. But want to push quality over quantity pretty much all the time. Maybe at the very end, right before your exam, then you start, knocking out more practice tests and more practice sets. But even then, you don't need to sit there, crushing 50 problems a day by any means. It's much more about spending all the time it takes to get something out of a problem, even if that means that you're reviewing the same problem for a half an hour or more. So we'll start by just doing a few different math problems and see what we can spin out from them from there. Getting a question before we start about study time frame, and that really varies from person to person. It depends on the most natural thing is, how far are you from your goal? Um, the farther you are from your goal in terms of absolute points, the more time it takes. And the higher your goal is, the tougher that climb is, right? In other words, going from, say, a 148 to a 158 is going to be easier for most people than going from a 158 to 168. Not because a 158 is, say, easier to get than a 168, although, I guess by definition it is. You still have to work for it. You still have to fight for it. But because at the top, you have to miss so few questions. And so I'll have people who are very, very good at pretty much everything the GRE tests, but they always find they miss a few questions. They make some mistakes, and most of us do. And so it's trying to like weed out those little things at the top that makes it harder. Um, and of course, it also depends on how many hours per day you have available to study. Usually, when someone's trying to make a fairly substantial improvement on their test, I usually recommend a few months at least of about 2 hours a day. But this varies widely and wildly from person to person. And not everyone has the time for that. Some people have a lot more. Some people are studying more or less full time. But I would say it's safe to allocate at least a few months with 2 hours per day, including a nice set of practice tests, intermittent practice tests at first every few weeks, and then weekly practice tests for about the last month before test day. So just a rough idea. Um, okay. Let's go ahead and try some problems. Um, We'll start with this one. Since this one is not multiple choice, what I'll ask you to do is just private chat me the answer. When you're done, we'll check in within about 2 minutes. But whenever you think you have an answer, whatever that is, even if it's a guess, and remember, even on non-multiple choice, you can guess. You can just figure out, since the answer is a fraction, you can figure out what kind of fraction might be reasonable and guess if need be. But go ahead and answer within about 2 minutes. Okay, here we go. Try it out. Okay, so let's check in. These rate problems can certainly take a long time, and sometimes they take longer than we'd like. But we really want to be careful about that because we've got to balance this across the rest of our section. And especially if we find the problem hard, we have to balance that against the fact that, hey, maybe I'll put in 3.5, 4 minutes to do this problem, but maybe I don't like this problem, and maybe my chances of getting it right are not that great. Um, Certainly, if I guess, I have a hard time because it's a fill in the blank, and I don't know how specific a fraction. Can I just easily guess something like a half or three quarters, or is it going to be something a little funnier, like 25 31st or something like that? Um, so it can be hard to guess. But the trade-off there is that I don't want to invest so much time in this that I'm stuck somewhere else. When in doubt, I'll move on because, of course, on the DRE, you can always come back at the end of a section and fill in any questions that you still want to spend a little bit more time on. So go ahead, and if you're here attending live, go ahead and private chat me an answer, even if it's just an abject guess, if you just have no idea. It might be worth taking just 10 seconds to say, do I know anything at all about the fraction that worker X does? Is there any kind of limit on that fraction? Because that way can narrow down your guesses. And if this were a multiple choice question, of course, then it might get you part of the way or even all the way to an answer. Sometimes when you just take a moment to think about what's possible, sometimes there was only one answer. Okay. Okay. So one thing we might think about, and this is a really common thing to think about with fractions, when I'm going to pick a fraction as an answer, whether I have to generate my own entirely like this, or whether I'm picking from multiple choice, I might think about two things that are common for fractions. Is it more or less than one, right? In some cases, you might have a fraction that's greater than one. Like, what's the ratio of the population of Japan to the population of, I don't know, Singapore or something like that, right? Here, I'm not going to have a fraction greater than one. Worker X certainly can't do, more than all of the work. So we know the fraction is going to be less than one, more than zero. But then we might also think about the fraction in relation to 1/2, right? So I could start with, okay, more than one or less than one. I'm writing the same thing twice, less than one. And so we could say, okay, so it's definitely 100% sure less than one. And then we could say, okay, cool. That's a terrible color to use. Let me try that again. It's black, less than one. And then we're going to say, okay, so then what about 1/2? Should it be more than 1/2 or less than 1/2? Now, what do we know about that? Given what we know about worker X, do we expect that if the two workers were together, X does more or less of the work than Y? Thoughts on that? So some different guesses in terms of, what the actual answer would be. Some of those guesses were answers. They're not all guesses necessarily, but some of them were less than half and some of them were more than half. Um, but what we can say is, yeah, X is faster than Y, and we have to be careful how we quantify things. At a glance, I might look at this and say, oh, X's number is lower. But what does that number represent? If that were a rate, right? Like if I'm going 20 miles an hour and you're going 30 miles an hour, then that lower number means that I'm slower than you. But for a time, it's the reverse. It's reciprocal, right? The lower my time is, the faster that means I'm going, right? And that's natural when we investigate it, right? Um, so if X is faster, then we'd know that X has to be doing more of the work, all else being equal, right? It's one thing if, I don't know, like X is going to do half the work and then to sit and wait, take a break, have a sandwich while Y finishes the job, right? And that might be what we do in certain circumstances, right? Or just variable amount of time if it's sequential, like a relay race. I'm going to run a certain distance. And if I'm fast, I just get done faster, but I'm going to hand the baton to you and you're going to run a certain distance, but I'm not going to run some of yours and you're not going to run some of mine, right? But when we're working together, and this is a really common situation for GRE word problems, we're working together until we're done. Whoever's faster will do more of the work. And so we can know with pretty clear certainty here that our answer has to be between 1/2 and 1. We okay with that? Right? So if we kind of fill this in, we could say, all right, I know my answer has to be more than a half and it has to be less than 1. If this were multiple choice, maybe all the answers would be there. Maybe I'd see, I don't know, 3/5 and 2/3 and 4/5 and 5/6 and things like that. It could, but I might see at least 1 or 2 answers that were outside this range, and then I know to discard them. Now, of course, this doesn't answer the question, but it gives us a way to narrow down, and I think that's one important thing to look at. So when I'm reviewing a question for insights, one thing I want to do is try to connect it to other problems like this that I've seen. So if you've done a lot of rate and work problems, you might recognize that we can put this into a formula: rate times time equals work or distance, right? So I might, one way I could learn from this problem is to do a chart. Rate times time equals work. And I can either create a job that's just, I can just write it as one job, one paint job, they're saying. The paint doesn't really matter, but okay. Or I can create an imaginary task so that I can make the rates, instead of fractions, I can make them integers. I'll show you what I mean. So one way to do this would be to say, okay, let's call X's work one job. This is the work that it would do in theory, although in the real problem, of course, neither of them is going to do a full job. But we'll just fill this in. X can do one job in 2 hours. So we know that X does 1/2 a job per hour. And then we know that Y can do the same job in 3 hours. So we could do the rate as 1/3 a job per hour. But you can look for alternatives. So one way that people often like to do these that makes it seem a little friendlier is we just create a number of things that they need to do. Like if we're talking about a paint job, maybe that's a number of square feet or a number of panels or something like that, right? Or we can just, since it's not, we don't really care about the units, we can just say a number of units. So I might say, hey, what if I just said that X does 60 units? That's the job, right? And so if it does 60 units in 2 hours, then it's doing 30 units per hour. And if Y would do that same 60 units in 3 hours, then Y's rate is 20 units per hour. And notice that these match each other. In other words, 20 is 2/3 of 30. And if you check it, 1/3 is 2/3 of a half, if that, it's a mouthful to say, right? But 0.33 is 2/3 of 0.5. Okay. So we can then say, all right, what do I do now? If they're working together, I'm gonna have to add those rates up. And this is one of like the central things. Like if you don't know this, then you're gonna have a lot of rate and work problems that bother you. So you want to make sure you have this idea of it, even if you end up doing the problem another way. You want to think about combining the rates. And the rule of thumb, or not even the rule of thumb, just the general rule, is that if 2 trains, cars, peoples, trucks, pumps, whatever it is, 2 entities work together for a period of time, and they're working toward the same, shared goal, not competing, right? Like who can get to the finish line faster, but they're both working toward the same result that they're both contributing to, then we simply add the rates. So if we're doing fractions, we'd have to get this in terms of sixths. A half is 3/6, a third is 2/6, and we'd say 5/6 job per hour. If we're doing this with integers, we could add the little units we made up and say, hey, this is 50 units per hour. What we want to get used to with a rate and work problem also is that the rates add, but the time and work typically don't. Because I'm not saying, hey, X works for 2 hours and Y works for 3 hours. Instead, these are kind of hypotheticals. I'm saying X would work for 2 hours if X was working by itself. And Y would work for 3 hours if Y were working by itself, but they're not. And so we're not saying that 5 hours passes. Far from it. It's going to be a less than either of the individual times, which ought to make sense, right? If you can do a job in 2 hours and I help you, whether I'm faster than you, slower than you, doesn't matter. If I help you at all, even if I'm just the tiniest contributor, then you're going to take a little less than 2 hours at least, right? So we should have a time that's less than either of the individual times. So if we do this with a fraction approach, and I'm doing both at once because I'm emphasizing review and seeing more than one way. I'd probably do these in a row in real review, but I'd say, okay, so if I'm doing one job, 1 divided by 5/6 is just a reciprocal thing. And I think one thing that you can get from these rate and work problems is this idea that rate and time are reciprocal. right? As rate goes up, time goes down, vice versa. And when the work is just one job, the one nice thing about a work of one job is that they are directly reciprocal. I'll show you what I mean when I show the 60 units as a job. Then I would divide 60 units by the rate of 50, and I get still 6/5 of hours, 6/5 hours, or 6/5 of an hour. But 50 and 6/5 themselves aren't reciprocals of each other, right? If you flip 50 upside down, you get 1/50th, not 6/5, of course, because the work is no longer one. But the idea is still there that they have a reciprocal relationship in that when rate goes up, time goes down. As time goes up, rate goes down proportionally, right? And so if you work twice as fast, you should take half as long. If you work 3 times as fast, you should take a third as long. If you work something that's not a nice integer like that, if you work, say, 5/3 as fast, you should take 3/5 as long. Okay. So this is something we want to be able to do. And then we'd say, okay, so wait, what is it that I wanted to know though? The problem with this, and here's where I might have to learn it by comparing to other problems. I'd say, okay, I've got a full chart, but what's the answer to the question, right? Imagine my dismay if I put in 6/5 as my answer and later I got it wrong and I went, wait, that doesn't make sense. That doesn't fit what I wanted at all. And it's nice to have these guardrails in place, right? I know my answer has to be between 1/2 and 1. So if I get 6/5 as an answer, I know something is up, because how can X do 6/5 of the work? X could do 6/5 as much work as Y does maybe, but 6/5 isn't the answer to any question that they're asking, right? It's not even really close to an answer that they're asking. They're asking what fraction of the work is performed by worker X. They're asking us to compare worker X's work to the total. The problem is that we've fallen for what I sometimes call the Sudoku trap, which is where we fill in a bunch of boxes, and yet we don't really know what we want or what to do with what we have. And so when I'm reviewing, I might look and say, hey, I did all this good work. Nothing I put down was wrong, except unless I put this as an answer, right? But so far, nothing I've put down, not a single thing has been wrong. But it hasn't led me to an answer yet. And so if I got stuck or frustrated or ran out of time, or if I had to guess, or if I guessed something that I had on my paper just out of desperation or what have you, then I'd want to look back and say, so why didn't I have an answer? So I'm curious, do we know, like, what do I need to do at this point to turn this into an answer? Right? 6/5 is definitely not what I want. It's an interesting piece of the problem, but how do I actually find an answer? Like, one really useful guardrail or protection that we can have in place on these is to set up in advance what it is that we want. And so if they say what fraction of the work will be performed by worker X, we'd want to say, okay, well, the question is asking for this. And so I'll make a little solution expression. I want to say X work over total work, or X plus Y work. And so often it helps for me to start in English or any preferred language, and then fill in those pieces as I go. Right now, though, the problem is, since I've done this Sudoku thing of filling in all the boxes, I don't know X's work. I wouldn't want to say one job, because X doesn't do a whole job, right? X would have done a whole job in 2 hours. So what I'm going to do at this point is either make a new chart, or ideally maybe realize that I never wanted to fill these one job 60 units things in the first place. Those were just to get me to the rates. And so if you're pretty comfortable with a rate and work problem, you might get those rates without writing this down. In other words, I would imagine that you could get pretty comfortable saying, hey, if it takes me 2 hours to do a job, then I do half a job per hour, and I don't need to write down rate times 2 hours equals 1 job to get there. If I do need to do that for now, that's fine, right? But long term, I don't want to have to do that. And I think the problem I got into is that I had too much of this filled in, right? Now I could also, again, just make another chart, and it's up to you which one you do, because we'll see we get into a little bit of trouble still. So now if I said, okay, once I found the 6/5 of an hour, I could say, okay, well, what happens then? That means X works for 6/5 of an hour. Okay. So if I multiply 1/2 times 6/5, I get 3/5 or 6/10, right? So I get 3/10 of a job, right? That's not right. Sorry. That's what I would do if I do, no, I have that right. Okay. Oh, I simplified 6/10 to 3/5, and then I put 3/10. I was going to say that's not right. So notice what I did there. I messed up for a second, and the reason I caught it is I knew that X needed to do more than half the work, and so if X only did 3/10 of the job, then obviously Y would have to do the rest, and that wouldn't work. So I'd say, okay, no, I need this to be 3/5 of a job. Okay, and then Y, at this point, we can guess that Y does the other 2/5, but we can prove it because a third of 6/5 is 2/5. A third of 6 is 2. So we have 2/5 of the job, and it adds up to one job. Thankfully, we don't have trouble adding these up because, of course, they do have to add up to the one job. And so then I just say, oh, X's work is going to be 3/5 of a job, and the total work, X plus Y, is going to be one job. And thankfully, 3/5 over 1 is not bad. It's just 3/5. That's my answer. So if you got that, or if you knew that it needed to be in that range, then great. But this is one way to do it. You might imagine that right now, this would take you too long. Maybe it would take you 3-4 minutes. I think it would be valuable to consider reviewing problems like this until you can do this full solution we just did in less than 2 minutes. You may or may not get there this month. You may or may not get there at all. Or maybe you're already there. Maybe you find this a pretty quick operation to do. So I'd recommend working on that. But there are other ways through this. And what I'm always doing is looking for ways to do things faster, easier, to do less work, right? So one thing we already saw is if I don't want to draw two charts, I might jump straight to the rates uh, in one chart and leave out the parts where I show the time and work that X and Y would have taken. I could also use the shortcut of working with real units. And so if I don't like that 6/5, or at least I don't like doing 6/5 of 1/2 and 1/3, you can imagine continuing the work we had of picking numbers and saying, all right, so if this is 6/5 of an hour times 30, I'm just getting an extra fifth of 30. That's 36 units. And an extra fifth of 20, that's 24 units. That adds up to 60. And you might like that better, right? Here, I don't think it's a substantial difference, but you might still like to say, hey, 36 over 60, pull out a 6, and you have 6/10 or 3/5, right? Keep in mind, by the way, also that the GRE doesn't care if you simplify your fractions. So if you answered 6/10 or even 36/60, you would still get the question right. If it's multiple choice, then you have to recognize which one matches your answer, which you might be able to do just by process of elimination. It's good to know, of course, how to simplify a fraction, but you don't have to. If you write down 36/60, you can do it. I wouldn't recommend being willfully weird, but imagine that the answer to a question number 2, and you put down 34/17. Still 2, you'd still be right. And so as long as it works, it counts. But we don't want to overdo that. Okay, before I look at one other thing with this, any questions on what we've done so far? So what I've tried to do at this point is connect this problem to other rates and work problems I've seen, other rates and work problems you might have seen. I've also tried to connect it to other fraction problems in that whenever we're faced with a fraction, we can think about what kind of fraction do I have? Do I have a proper fraction between 0 and 1? Do I have a fraction greater than 1? In some cases, maybe do I have a negative fraction? Usually when they say what fraction of something, they're not going to say negative because that doesn't make a lot of sense. But what kind of fraction are we dealing with? And then is it, a small one, like less than 1 or greater than, less than 1/2 or greater than 1/2? This shows up a lot with things like probability. You may not know exactly what your chances are of, winning the Powerball. Maybe you'd like to believe they're high. Or, you might not know the chance that it'll rain 3 days in a row or what have you, right? But you might have a rough idea of whether that thing is rather likely, like more than half, or very unlikely, close to 0. And that can make a big difference, even when you're not working with multiple choice. Okay. But I'd also like to be able to connect a problem that I'm doing to other types of problem entirely. And there are other ways to see this than just as a rate and work problem. Once we recognize that rate and work are reciprocal, we can also think of going from time to rate to work in sort of a weighted average sense. And one way we can think of this is that, again, since X has a lower time, it's going to have a faster rate, and the amount of work that X does is proportional to that. And if we see that, then we can do this quite quickly. So if I say, for instance, that X make this bigger. X takes 2/3 as long as Y to complete a job, right? We agree with that. If X would take 2 hours and Y would take 3 hours, it's taking 2/3 as long, right? But because rate and time are reciprocal, that means that X works 3/2 as fast as Y. With me? Takes 2/3 as long, it works 3/2 as fast, and we can take those 3's and 2's and just do it directly, right? If I increase my speed on the freeway from 60 to 80, then it might be pretty clear I'm going 80/60th as fast. But it could also be said that I'm going to take 60/80ths or 6/8 or 3/4 as long to get where I'm going if I increase that speed, assuming I don't, get pulled over by the cops, right? So I can set up those kind of reciprocal relationships between rate and time. And then I can say, okay, that means X will do 3/2 as much work as Y. Now, that doesn't have to be true. Like I said earlier, depending on how the problem is set up, it could be that X does half the work and stops, or X does even less than half the work. Maybe X only works for 15 minutes and then Y finishes the job. But if they're working together for the whole time, then X will do 3/2 as much work as Y. And so then I can think of this as a ratio. For every 3, whatever square feet that X paints, Y paints 2. So how many get painted? So then I could say X over total is 3 out of 5. So in short, I can say that X is 3/2 as fast as Y. So it does 3/2 as much work. But then when I think about that in terms of totaling a ratio, I could say X does 3/5 of the work. And this relates to things like weighted averages, right? Imagine that I say something like, if we go with a typical American grade point system where a B is 3.0 and an A is 4.0. Okay, and then what if I said something like, I have 3 A's for every 2 B's, right? Then again, I would say I have 3/2 as many A's as B's. 3/5 of my grades are A's and 2/5 are B's. And then if I have a line from B at 3.0 and A at 4.0, I could say that I'm 3/5 of the way along that line. I'm closer. I should expect my GPA to be above 3.5. That's also a weighted average or fraction kind of thinking, that I should be closer to A than B. And then specifically, I can kind of draw a line. You could even think of it as a vector if you're into that kind of thing, and say, hey, I'm pulled 3 in this direction and 2 in this direction, and out of 1.0, that's 3/5 of the way from here to here and 2/5 of the way from here to here. So what's 3/5 of 1? 0.6. My GPA is at 3.6. What's 2/5 down from, of 1, from 4? Also 3.6. And so this same kind of reasoning can be used to think about rates and work, can be used to think about weighted averages, statistics problems, proportions, things like that. And the more you look for this kind of stuff, the more you can start finding it. This particular thing may not do it for you, may not have occurred to you, or it may be how you think all the time. But I think finding ways to expand that is very important. And looking for this in everywhere, right? I once did one of these on just everyday math, for the tests. Might have been a GMAT one, but I was thinking about how, I'm doing this when I'm working out, right? If I'm working out on a treadmill and I say, if I'm going this fast, and how would I average speed? Okay, when I'm going 8 miles an hour, it's this many per then this would. I'm doing this all the time because, I'm that kind of weirdo, right? You don't have to be as weird as me, or you maybe you're weirder, I don't know. But you can use some of that same kind of thinking to apply to a lot of the different tasks you're doing. Okay. Thoughts, questions, freakouts, anything on this before we move on? Okay. Let's try another problem, and for this one we'll do some extensions of it after we do the first one. So this one, just for anyone who might be new to the GRE, is a quantitative comparison. So I have the answers down below. By the way, all the problems today should be, I think I'm doing all originals. So basically problems I wrote for this workshop that you won't see in the official guide or in our 5-pound book. So, bonus questions today. But the idea is answer choices. If you haven't seen these before, A means quantity A is always greater no matter what. B means quantity B is always greater. C means the two quantities are equal. D means you can't determine the relationship. We're not going to pick that on this one. Anytime where there are real numbers, maybe I can't determine the relationship. Maybe I don't know the answer, but I know there is one. Like one of these is definitely bigger. So the answer must be A, B, or C. We can cross off D immediately on a question that's all just straight numbers. But let's go ahead and pull in your answer when you have it. So I'll give you the poll. Unless you're on a mobile device, you should be able to pull it right now. Okay, take a moment to try this out and then we'll talk. Okay, so we'll stop there. I usually target around 1.25 minutes on these quant comps. They're meant to be a bit faster than the regular quant. Go ahead and pull in an answer. If you pull in, you might be the first one to get this right. Sorry, everyone who's pulled in. So far, no one has this. Interesting. So go ahead and pull in an answer if you haven't already, and if you're watching this as a recording, commit to an answer. So we've got an interesting principle here. Clearly, we're not going to calculate these, right? You do have a calculator, but it's got its limits. It maxes out at 8 digits, and even if these were small enough to fit on your calculator, there's no exponent key, so you'd have to do 2 times 2 times 2 times 2. You don't want to do this, of course. And if this did fit on your calculator, of course, they'd make it bigger, so it didn't, because the GRE is not testing whether you can punch numbers into a calculator. So we have to have some kind of principle. One thing we might think about is quantity A has a 60th power. So that's clearly the highest power that we see on the screen. That's in A's favor. But then it tails off so sharply. And as I'm sure you realize, like these are huge numbers, right? So 2 to the 30th is a whole lot smaller than 2 to the 60th. 2 to the 30th is still a lot. It's over 1 billion, right? Rough rule of thumb is every 2 to the 10th is 1,000. So 2 to the 10th is, what is it, 1,024, and 2 to the 20th is 1,024 squared, so over 1 million, and then 2 to the 30th would be, 1,024 times that, so over 1 billion. 2 to the 60th, do that 3 more times, so you got trillion, quadrillion, something in the quintillion something range. Not something that's going to fit nicely on a calculator, not something we need to think too deeply about. Okay. So that's what we have in quantity A. Quantity B starts a little smaller, but you might not seem like it's that much smaller. 2 to the 59 is still pretty big. And then it doesn't tail off so much. You got 2 to the 58, 2 to the 57, right? If I simply added the exponents, I'd get 60 plus 30 is 90, plus 10 is 100 on one side, whereas on the other side, I'd clearly have over 150, right? So clearly B has larger exponents. And if this were multiplication, B would win. Right. So just again, in terms of reviewing for principles, sometimes it's just reviewing for the sheer rules of it. Right. If I had 2 to the 60th times 2 to the 30th times 2 to the 10th, then I would add the exponents, right? I would say, oh, that's 2 to the 100th. And similarly, 2 to the 59, blah, blah, blah. I would add those and I would get whatever that is, 100 and, 170 something, right? So, clearly B would win. But B does not win. B does not win, and it's actually not close. A wins by a fair amount. How is this possible, right? Let's make sure we have a principle here. So one thing we want to think about is how exponents work and how doubling in this case works, right? If we think about our exponents, right? 2 to the 1 is 2. And you even get doubling from 2 to the 0, right? 2 to the 0 is 1. Even that doubles, right? 1 doubles to 2. And if we went to 2 to the negative 1, that's a half. Even that is a doubling, right? 2 squared is 4. 2 to the third is 8. And as they double, naturally the gulf between them increases. Imagine you had an investment that keeps doubling. That's great, right? And every time it doubles, your wealth increases by a larger amount than it did last time. Now I have $4 more. Now I have $8 more. Now I have $16 more. The gulf between them keeps growing. So what does that mean? That, what did I say 2 to the 60th was? Like a quintillion? Well, then what's 2 to the 59? Half of a quintillion. And so 2 to the 60th is, what is that? Roughly like 500 quadrillion larger than 2 to the 59th. Again, you don't have to think in quadrillions and quintillions, but you see my point, right? If 2 to the 60th is basically the same as 2 to the 1 plus 59, that's saying it's 2 times 2 to the 59th. So 2 to the 59th is a vast number. If you won that much in the lottery, well, you'd be the richest person in the world. Is there even that much money in the world? I don't know. And if you got double that, right? Well, that would be a whole lot more. And so one thing that's, I think, really important to recognize is even though 59 and 60 are very close together, 2 to the 59 and 2 to the 60 are not very close together. In logarithmic exponential terms there, but in terms of actual size, 2 to the 60 is vastly bigger than 2 to 59. With me on that? So then we say, okay, but isn't 2 to the 58 also really big? And isn't 2 to the 57 really big? And isn't, in fact, 2 to the 58 many, 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 many times bigger than 2 to the 30th or 2 to the 10th? Who cares about those, right? Well, let's do something interesting for a minute. Again, to review and get something more out of a problem, don't just look at, did you get the answer? What if I took some of these out? What if I took it to the extreme? What if I got rid of these two numbers entirely? What if I just compared 2 to the 60th to 2 to the 59? Just for kicks, let's call 2 to the 60th, let's give it a variable name. Let's call this x. If 2 to the 60th were x, what would 2 to the 59 be? If 2 to the 60th is double of 2 to the 59, this would be x over 2. And what would this be? Half of that. And what would this be? Half of that. So let me ask you, would you rather get x dollars or x over 2 plus x over 4 plus x over 8? So what is this going to be, right? Half plus a fourth plus an eighth. 4/8 plus 2/8 plus 1/8 is 7/8. Right? And in fact, what if I not only got rid of the 2 to the 30th and the 2 to the 10, what if I kept going? What if I added 2 to the 56th and 2 to the 55 and 2 to the 54? Now, surely almost no one would guess anything but B. But it would be, in a sense, a guess, and it would still be wrong, because look what's happening. What if I add a 16th and a 32nd? Notice that I'm approaching a limit of 1, and I'm never going to get there, right? Because now I'll be at, what is that? 14 16ths plus 1 16th is 15 16ths. That's 30 32nds. That's 31 32nds. I'll basically always be with my numerator 1 less than my denominator. And so this one would now be, why is it not letting me write? This one would now be 31 over 32. So even if I got rid of the 2 to the 30th and the 2 to the 10, which are kind of a distraction, honestly, and if I kept going 2 to the 59 plus 2 to the 58 plus 2 to the 57 all the way down, I would never get as much as I had in the first one. So a couple principles you can get from this. One is that we have rules for multiplying exponential terms, right? But not for adding them. And don't get me wrong, I'm not saying you can do whatever you want when you're adding. There's no mathematical reasoning to be done or no rule. But there's not like a simple way to say, oh, 2 to the 60th plus 2 to the 30th plus 2 to the 10th is 2 to the blah blah blah. In fact, it's not 2 to the anything, which we'll come back to. Another thing here is that since every exponential term is a multiple of those below it, adding lower terms doesn't make our value grow much. One way you can think about that is think about a number like this: 1,111,111. What is that? That's 10 to the 6th plus 10 to the 5th plus 10 to the 4th plus 10 to the 3rd plus 10 to the, all the way down to 10 to the 0. The idea is like, okay, so that's what that is. 10 to the 6th, 10 to the 5th, 10 to the 4th, etc., all the way down. And notice that it's nowhere near 10 to the 7th, right? What would 10 to the 7th be? 10 million. And so what we can generally say is we'll get more than our highest term when you add, I'm going to clearly 2 to the 59 plus 2 to the 58 plus 2 to the 57 is more than 2 to the 59. And clearly 2 to the 60th plus anything positive is more than 2 to the 60th, has to be, right? We'll get more than our highest term, but less than the next term up. So what do I know about this sequence? The original sequence I had before I got rid of 2 to the 30th and 2 to the 10, I know that it's going to be more than 2 to the 60th. I think we'd all agree on that pretty quickly. It's more than 2 to the 60th because I added. But it would be less obvious to us maybe that it would be less than 2 to the 61, right? And so we have a prediction we can make here without doing a lot of calculation, because calculating here is going to be pretty much impossible for us. We know that this is in here. And this sequence, whether we have this expanded version that I did, or whether we talk about the original version that we were presented with, this sequence, we can do the same thing. We can say, okay, this value has to be more than 2 to the 58th, 2 to the 59th, because I added to that. But it has to be less than 2 to the 60th. So if you want to get fun and talk in terms of quintillions, right, it's less than the quintillion mark and more than halfway of that. Whereas the second one is more than the quintillion mark and less than 2 whatever quintillion it is. Again, that's just an estimation, and who cares about those names, right? But now we can say, oh, roughly speaking, right? We can just look at the top term and say, ignoring all that other stuff, 2 to the 60th is double 2 to the 59. And sure, the 2 to the 58 and 2 to the 57 are bigger than the 2 to the 30 or the 2 to the 10, but that's the pocket change, right? It's like trying to compare 10 million to even something like this. What if I had 10 million versus 1,587,499? Sure, I have bigger values in those lower levels than in the 10 million where it's a bunch of zeros, but it's still not even close, right? It's no competition at all. And so that's how we can see that this has to be A. Okay. Okay. Questions on that? Then on the theme of connecting to other content, I think one little move we have here that's not as directly connected to exponents is that when you have something complicated to deal with, whether it's a function or a factorial or an exponent or a quadratic or something like that, sometimes you can boil it down to just be that thing, that number, that an x, right? And so one thing that I think was kind of a cool move to do here was to say, all right, let me call 2 to the 60th x. And then it's really easy to think about this as half of x and a quarter of x the way we did. I could think about the others, right, if I wanted, but it would be really hard. I'd have to say 2 to the 30th is x divided by 2 to the 20th. It's like it's really just doesn't matter, right? It's basically like a millionth of x. So I just don't care about it, right? And then 2 to the 10th is like a millionth of that. And so it really, then you could really just see how insignificant that is, right? It just doesn't matter to the problem. X divided by a million, and then this is X divided by, a billion. And so those are just, they might as well be zeros, even though they're huge amounts, right? If you give me 2 to the 30th dollars, sorry, I probably wouldn't teach another of these workshops. I'd find other things to do. I would. Judge me if you will. But in the context of 2 to the 60th is nothing. Right. Okay. That all right? So things you can do, when you're trying to simplify something down, right? And I've seen this with like factorials, right? Maybe I'm trying to reason about something like you know, 38 factorial, right? And then maybe somewhere else I'm seeing something about 36 factorial. And I can treat 36 factorial as a number, or I can just treat it like some quantity. So I can call 36 factorial x, or I could even just say 38 factorial is 38 times 37 times 36 factorial. So I could just substitute something in, and instead of worrying about what 36 or 38 factorial is, I can just recognize, hey, this number is that number times these two things, right? And maybe I can get a sense of that, Imagine they asked you to compare 38 factorial with 2500 times 36 factorial. And then you could say, oh, well, 2500 is 50 times 50. And that's more than 38 times 37. So this one wins, right? And so I can use that to replace pieces instead of actually trying to think about calculating the value. Okay. Um, and so you could even see a problem like this presented this way. And this problem, I think you would like much better, right? If I said, hey, what's x versus x over half plus x over 4 plus x over 8, you would just do the math and you'd find that x is bigger and it would win. So you get to turn this exponent problem we did into that, right? Similarly, if you had smaller numbers, these might be small enough where you would just calculate. You could just barely, whether you just know this stuff or you have your calculator, you could just find out that 2 to the 10th is, 1024, and you could find 2 to the 5th, 2, 4, 8, 16, 32. You could add it up. And so if you did that problem, let's say you did this by just brute force, right? You just said, okay, this is 1024 plus what I just say, I have to think about it, 32 plus 4. And here I'd say, 512 plus 256 plus 128. Yeah, I have some of those memorized. Maybe you do too, but you don't have to. You can always break them out. But then I could say, okay, yeah, this one's bigger. But if I get this problem right, and then I think, cool, that's what I'll do every time, what happens then when the numbers are vastly larger? And so I'm often thinking about if I did something like just by finding all the numbers, that's really cool when that's findable, right? It's like combinatorics. If there's 5 ways to do something, maybe you can list them all out. If there's 305 ways to do something, that's not how you're going to do the problem. So I'm always looking for a more efficient way to do even the simplest problem, even how to add up 1 plus 2 plus 3 plus 4 plus 5. Sure, I can do that in my head, right? So can you, I'm sure. But if I recognize a principle, hey, the average will be in the middle, it'll be 3 multiplied times the number of terms. Then now when they ask me to add up something larger, I can do it, right? When they say, hey, what's 1 plus 2 plus 3, all the way up to 900, I could say, oh, the middle term will be, let's see, 901 in half. So the middle term would be right between 450 and 451. So it'll be 450.5. And there's 900 numbers. So I'll do 450.5 times 900. I will enter that on my calculator, and that'll be the answer, right? I'm not going to try to add up those numbers, thankfully. Okay. Let's try one more thing here. Once again, I'll give you a little time to try it. This one, you can have a full 2 minutes if you like, because it's a full multiple choice problem. So I'll give you a poll, and we'll try it. Okay, go ahead and put in an answer, even if that's a bit of a guess, that's okay. There's another stumper. So far, no one's got this one right. But I do want to congratulate folks for successfully bypassing a very tempting answer of E. Maybe it wasn't that tempting to you, but I'm glad we're not just saying, hey, what's the largest number? Because divisibility doesn't work that way, right? 30 is divisible by, well, 30 and 15 and 10, but it's not divisible by, 9 or by 7, right? And so we don't always want to simply think about what the biggest number is, but what has the factors that need to go in. And one general principle for divisibility is that something is a multiple of another number, it's divisible by that number, it's the same meaning, if it has all the prime factors that are in that number. So we might think about what's in 30 factorial. Now 30 factorial, if that's not familiar notation to you, as we were just seeing earlier, is basically 30 times everything, every integer lower than that all the way down to 2 or 1 if you want to be complete, but of course doing multiplying by 1 doesn't do anything. And like I was showing earlier, factorials build on themselves. So if I know that, say, 2 factorial is 2 and 3 factorial is 3 times 2 is 6, I can say that 4 factorial is 4 times 3 times 2 times 1 and just do that out. It's 24. Or I can just do 4 times 3 factorial, right? 4 times 6 is 24. And so if you know your first few, right, a lot of folks end up memorizing the first few factorials if they end up doing these a lot. 5 factorial is 120, 6 factorial is 6 times 120, right? So it's going to be 720. And then, so if I then have something like 10 factorial, that's getting a little uglier than I want. I don't necessarily want to calculate 10 factorial, and I don't have it memorized. If you do, hats off to you. But it would be this, right? And then maybe I have cancel some things or find some things out, right? So 30 factorial is going to go all the way down. I'm not going to find out what it is. I don't care what it is. I'm not trying to figure out the number itself. But guess what? It's a multiple of 170 million. It might be quite a bit more than that, but it has at least that in there, because E is not the answer. So it is divisible by 30 factorial. I also am glad no one picked A. This is a good general principle you can use for a lot of problems when you're dealing with a except question, a not question. Well, if A were not divisible by 5 to the 5th, then it also wouldn't be divisible by 5 to the 7th, because 5 to the 7 is just 25 times 5 to the 5th. And so for 5 to the 5th to be out, you'd have to have another answer out, and there can't be two answers. So 5 to the 5th can't be our outlier. But interestingly, neither can 5 to the 7th, because guess what? This has 1, 2, 3, 4, 5, 6, 7 tens, and 5 to the 7th goes into 10 to the 7th. And so B can't be it either. So answer actually has to be the more modest C or D. Interesting. Okay. So how would we know what goes in here? And how would I recognize, like, for instance, I crossed out E just to tell you, but I haven't proven it at all, right? So how would I know that 30 factorial is divisible by 170 million? Am I supposed to do all that multiplication? No, right? Instead, this is a really common situation. In fact, I was just talking to someone the other day about a problem they saw that tested this among other things, and they were just thinking, like, how was I supposed to do this in 2 minutes? I think we were talking about at the beginning of the workshop today, and it's partly just like having seen it before. I think much as I like to look smart, I would love for people to think that I'm super clever. I have to admit that a lot of times when I'm able to do a question quickly, it's partly just because I've seen something just like it before. And it, makes my job a lot easier. It doesn't necessarily require me to be a genius, right? And in many cases, there are things that very few people, if anyone, would just figure out on the spot. That most people who are doing it have seen it before. You're not going to, invent a new type of math in the middle of the GRE, right? Even when people did that, Isaac Newton was sat there and developing calculus so he could do the astronomy work he wanted. He didn't do it in minute 45 seconds, to my knowledge. So what is it that we're supposed to see here? That if we're trying to find fives or tens, we can just look for where fives or tens fall in this number, right? So what is that? How many? So for instance, how many tens are in here? how many powers of 10, 5 or 10 are in 30 factorial? Well, a 10, of course, is 5 times 2. And so we really want to know how many pairs, okay, how many pairs of 5 and 2 are there? But can you agree that there's going to be more 2s than 5s, right? Every other number is going to have 2s in it, and most of them will have more than one, right? We have 2, 4, 6, 8, 10, 12, right? And every other one of those is at least a multiple of 4. We're going to have plenty of 2s. We have plenty of 2s, right? The limiting factor is 5s, right? So the real question then becomes, and that's what A and B are addressing too, how many powers of 5 are in here? And so then I can just think about, all right, well, which numbers are even multiples of 5? I've got 5, I got 10, 15, 20, 25, and 30. And so if I'm trying to count up powers of 5, I could say 5 is 5 to the 1, 10 has 5 to the 1 in it. Here's 1, here's 1, here's 1, here's 1, there's 6. And then, oh, wait a second, 25 is 5 squared, I've got 2. And one way I can catch that pretty quickly is that when you're counting by 5s, every fifth number will be a multiple of 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Of course, we've known, most of us, how to count by 5s for many years, right? But every multiple of 5, every fifth multiple of 5 will be a multiple of 25. And the ones in between will not. 5 only has one 5. 10 only has one power of 5, right? 15, 20. In other words, 5 is 1 times 5, and 10 is 2 times 5, and 15 is 3 times 5, 20 is 4 times 5, but none of them have a 5 times 5 in them until we get to 25. And then the pattern repeats. You're going to have 30, 35, 40, 45, and then not until 50, another 5 away, do you get another 5 times 5 in there. And you have to do that pattern 5 times before you get 5 to the third. So, and this is true, what I'm going to say applies to 5s, but it could apply to any number if you just substitute the different number for 5, right? Every fifth integer is a multiple of 5. Every fifth multiple of 5 is a multiple of 5 squared. Every fifth multiple of 5 squared is a multiple of 5 cubed, et cetera. And you can do the same thing for 3s or 10s or 17s or whatever. Every 17th integer is a multiple of 17. And every 17th multiple of 17 is a multiple of 17 squared, et cetera, right? So we can use that to find stuff. So what this tells us is, okay, that's 1, 2, 3, 4, 5, 6, 7. There are 7 powers of 5. This means 30 factorial is a power, or is a multiple, not a power, is a multiple of 5 to the 7 and of 10 to the 7, right? Because it's got 7 5s and it has a lot more than 7 2s. So we're good on 2s. And so we know that A and B go in, and we know E goes in because this is just 17 times 10 to the 7. And 17 is certainly in my list, 30, 29, 28, 27. Any prime that's in 30 on down is in there, right? 17's in there. So I just have to look at what's left and what makes it up. 33 is 3 times 11 times 10. Even if I don't break 10 down to primes 2 and 5, are 3, 11, and 10 on my list? Absolutely, right? You could also just say it's 30 times 11, right? 30 is in my list, of course. It's 30 factorial, and so is 11. So D is included. So why is C not included? Well, if I break 185 down by 5, I can do that by hand. 185 divided by 10 is 18.5. So 185 divided by 5 is double that, is what is that, 37? Or I could do it on a calculator real quick, just pull it up, 185 divided by 5. So this is 37 times 5. Well, there's no 37 in 30 factorial, right? Just even though this is an enormous number, there's no prime factor of 37 because it's made of the numbers from 30, 29, 28 down. None of them are as large as 37. And since 37 is prime, you can't build that out of other building blocks, right? You can't make 37 by multiplying, 2 smaller numbers. And so that's our answer. If you got that, hats off to you. If not, totally understandable, but you then can know this kind of trick for next time. So what am I thinking of? I'm thinking about the content of just how to deal with factorials, the explicit content that is testing. There's the general number properties idea of like, hey, every nth number is a multiple of n. And every nth multiple of n is a multiple of n squared, et cetera, that you can use to count stuff up. And then there's the idea that I've seen quite a bit. They might ask, for instance, how many zeros does this number end in, right? So if you ask, I don't know what 30 factorial is, but if you ask me how many zeros are at the end of it, 7, right? It's not 7, it's not 170 million, it's a lot more than that because it's 10 million times everything else in 30 factorial that's not a 10. And that's a lot, right? All the 3s and all the 5s and all the 7s and all the 11s and all the extra 2s and the 13s, et cetera, all multiplied together. So it's way more, in many places more than 170 million. It's a much, much bigger number than this, but it's going to end in 7 zeros. So you can remember that pattern. And so that's what I'm trying to get at with this is that most of the problems you see, especially hard problems, but even some of the easier ones, most of the problems you see are going to represent more than one kind of math thinking, more than one kind of rule, more than one kind of principle. And if you spend time to really juice these for all they're worth, right, it's much more valuable. You could say, oh, today's workshop was kind of a ripoff. They only did 3 problems, right? Although I threw in a few bonus pieces, right? That's one way to look at it, and I understand that perspective. But I think if you sat down on your own to study for an hour and you only did a handful of problems like this, but you had some principles to take with you that next time you saw them, you'd remember and that would stick with you, that would be a big difference, right? There are a lot of rules that I cannot forget. And not just, yes, of course, I've been teaching this for years, and that sure helps me to remember these rules. I have to keep saying them, right? But I think some of these rules, once I learned them, I would have remembered them even if I had gone off to just, write poetry or what have you, because once you understand why they work, once I understand why a triangle's area is half base times height, or why a trapezoid's area is base 1 plus base 2 over 2 times height, once I understand why, it's much harder to forget. uh, you know, what is it, 24 years ago now, I had to teach a 5th grader how to find the surface area of a cylinder, and I didn't know myself. And I had to find out and teach this bright 5th grader how to do it. And once it made sense to me, oh, it's a can's label plus the 2 lids of the can. I can't forget it. You'd have to, do some serious damage to my apparatus up here for me to forget it. And so we're trying to connect these pieces and make this test make more sense. And I think that's much more valuable than just doing another time set. Okay, well, hope some of you felt the same way. Stick around if you have any questions for me. Other than that, best of luck with your studies and with your test. Thanks, everybody. And if you want to check out any of our classes, remember you can check out any of our class 1s for free and see what we're all about, see what we have to offer. So I'd love to see you around. Thanks all.